Okay, this is an effort to kind of maybe clarify some of the stuff that we did on our lab last Friday, this little troubleshooting exercise. This is a simulation program called Multisim. And what I've done here is I built a circuit. This is essentially the same circuit that we built in class. Uh, you have a 1K resistor here in series with these two 1Ks that are in parallel, and then that's in series with this. So we learned that two parallel resistances of equal value in parallel are half the value of one resistance. So the equivalent resistance of these is 500. So you would expect the voltage drop across these 1Ks to be twice the voltage drop across these. So I've got some multimeters here. So I'll go ahead and hook up the meters so that you can see. I didn't want to hook them up first because there's a lot of lines in there and you might get confused. But all I'm doing is, and it's really kind of redundant to put a meter across both of these resistors because you're going to measure the same thing on both of them. But this will just prove that. Okay, now my meters are all connected. I come up here, I switch my circuit on, and we have a total of 12 volts. And I'm getting 4.8 volts here and here, and 2.4 across each of these. I really don't need to have two meters here. They're going to both read the same thing, but I just wanted to make that clear. When you add all these up, they equal the source voltage. Okay, so that's part one. The next part is I'm going to turn the circuit off, and then I'm going to introduce some problems into this. If I double click on this resistor, I have an option to put a fault in here. First fault I'll put is an open. And I'll put an open between pin 1 and pin 2, so this component should be open. Now if what I told you is true, that means that all the electrons are here, none can get over here, which means that you're going to read the total 12 volts between these 2 points, because that's the potential difference. You should read 0 across everything else because there's no current flow in the circuit. Well, this is a software-driven environment, so it is showing you almost 12 volts and very small voltages across these other components. In reality, you would see all the voltage dropped here and very little dropped over here. So now let's try a short circuit. Okay, now what we should see with a short circuit is you should see very little voltage dropped here, and you would see the remainder dropped across these two components. Well, these essentially are one component, two resistors in parallel. So you should see, this is as if you have a piece of wire. You should see very low here. You should see probably about 8 volts here and about 4 volts here. Okay, in this case, it's showing us 8 picovolts, which if you remember your metric prefixes, pico is 10 to the minus 12. So that would be an 8 with 11 zeros in front of it, volts. And essentially, that's 0 volts. And it's so small that it's just showing 4 volts here, 8 volts here. So those are the two things that would happen when this one is shorted and open. So I'll go back and I'll fix that so that there are no problems. Okay. So let's try let's go down the line. We'll try R2. If I go ahead and set a fault in R2 of an open circuit. Okay, now it's as if this resistor is no longer there. The only path the current can go is through here. So it's going to go through this resistor, and then it can't go up through this one because we just opened it. So it's going to go through here and then through here. So now what you have is you have 3 equal value resistors in series. So I would expect to see about the same voltage drop across each of them. But because the software tries to, you'll probably see something different here, but let's go ahead and try it and see. Okay, we have slightly less here because it is still allowing for some current flow through this, even though it's a tiny amount. For all practical purposes, you have the same voltage drop across all three of these components. So now let's try the other option, a short circuit. So now with a short circuit for R2, the electrons are going to get to this point, and they're going to have a choice of which direction to go. Well, if this is a short circuit, that's zero resistance, or close to it, so all or most of it is going to go this way. The difference in potential across a short is very close to zero. So we would expect to see a very small voltage drop here, and the rest of the voltage dropped across the two good resistors. So here we have 6 picovolts, and remember I said pico is 10 to the minus 12, so that's like 6 with 11 zeros in front of it. And you have 6 volts here and 6 volts here. So you basically have 0 volts dropped across these two. So that's the situation if this resistor, if R2 is shorted. Now if you do a short and an open for R3, you're going to see the same thing as we just saw. So if R2 was good and R3 was open, you would see equal value voltages across all three of those. If R3 was shorted, you would see the same thing we're just looking at now. This is a situation where if either one of these are shorted, they're both shorted. Okay, so let's remove the fault for that guy. And the last fault would be over here with R4. This should be a lot like what happened over here. In the first case, if we put an open, whoops, I have to tell it where to put the open. Okay, now if we put an open, the electrons go through here, they go through here, they go through these guys. They get to this point, they can go no further because you have an open circuit between these 2 points. So we would again expect to read almost the whole source voltage here. And because the simulation tries real hard to duplicate the real world, there's a tiny current flow that's going to happen. So this looks just like it did before with this resistor. You have almost all the voltage dropped here, very small amounts of voltage on these other components. And again, the reason you see this really small, you don't see the full 12 volts is because the simulation is assuming that the open resistor still has some current flowing through it, even though it's probably really, really, really small. Okay, so that's the simulation illustrating that concept. Take a look at this. Let me know if you have any questions. Bring them with you to class, and we'll figure it out.